Thank you very much. What Critics is doing is we are looking into attacks of various sort and of various sophistication. And if you plot, say, attacks which we have observed over the past few years, then what you see is you see an increasingly sophistication of the attacks. At the same time, you also see a very much decrease of the skills which are required. So essentially, nowadays, every script kit can go to the darknet and download all the sophisticated attacks, like distributed denial of service attacks, the scripts to run them, and also kind of purchase the compromised units that are already around there and simply run the attacks. In the past few years, we have seen the hardware level attacks up here, so we also need to start thinking about those. Looking at this picture, we will also have these nation-state hackers, so pick your favorite 3 or 4 letter organization who is able to hire the best people in the world, gives them the best tools, and break into any kind of system. Now, what Critics is doing, we are looking into fault and intrusion tolerance, we are looking into resilience and security and safety, of course, which I think I'm preaching to the converted while this is a good idea to do so. So let's go to my talk. In my talk, I would like to share with you my view on cyber resilience for cyber physical systems. I would, of course, we have all these kind of systems in mind, like drones, satellites, even systems which you might not think of, like wastewater removal, because if you manage to kind of avoid your wastewater to be cleaned, you can easily get illnesses and get most of the population eradicated by this. So even benign system might turn out to be quite tricky when someone mounts a cyber attack against them. And then, of course, the focus of this talk will be autonomous cars or collaborating cars, because it's so easy to explain all the stuff which we are doing on the example of these cars. I would like to give you an intro, and that's the thing where I said, please fast forward me if you already know all the stuff. And then I would go to the subtitle and tell you how a little bit of cheating allows us to be much more efficient in the number of replicas. But then, of course, that's for really controlling things, for controlling the cyber physical system, for making sure it flies, it drives, it kind of stays where it is. It doesn't tip over. But then you also have the situations that cars need a lot of complex functionality. And I mean, Huawei has this nice picture because they actually put all the autonomous driving functionality in one of the she boxes. So following 3F+1, that means you would drive with 4 she boxes on top of your car just to tolerate a single fault. Not a good idea. So we have an idea how to tackle that. And then, since Nuno started it last week, I would also like to talk a bit about one other topic, which is completely unrelated to this talk, and I just sneaked it in. So if we have time, we will go through that as well. Now, of course, we have a problem because we are terribly late. We promised the world in '57 that we will have autonomous driving. I would say the pictures have changed, the rendering improved, but I still believe we are as far as away from autonomous driving as we have been at that time, at least when it concerns safety or even cyber resilience. Now, when it comes to cyber resilience, we have already an inspiration from Hollywood. So Fast and Furious 8, someone hacked into a car electronics system and managed to be able to control the entire fleet and did a spectacular nonsense, which was nice for the film. Now, the problem is, if you look at the way ADAS systems are built and how the ADAS market looks like, you have essentially 4 suppliers. Bosch, Denso, Conti, and I always forgot the 4th one. They are sharing the market. So if you manage to break into a Bosch system, you are quite likely in control of a large bunch of cars. And I'm not sure whether Bosch or one of the others, I'm picking the German one because I'm a German, so I'm not sure whether that really is robust against the cyber attacks which are out there. And of course, we have seen researchers already trying out one or the other thing, like sitting in the back row of your car and steering it remotely while the journalist was in front. Now, This is the part where the fast-forward thing starts. So whenever you say, I know that, then I'll just skip over it. So how do we cope with cyber attacks to autonomous vehicles? And I mean, the first thing which we have to understand is how such a vehicle works. The first thing is we need all the car internal things happening, like battery control, which nowadays is quite aggressive to get the last bit of power out of your battery and be able to drive something like 300 kilometers or so. You need engine control, you need all the kind of things which are happening already in your car, even if the autonomous part is actually sitting here, or hopefully sitting there. But then in addition, you already have nowadays in your cars all kinds of sensors that you will later on also need for autonomous driving, like cameras to watch the front and rear, also the sides, LiDAR to have a view, the long-range radar, which gives you collision information for autonomous driving. And now if you look at the stack to actually drive a car, then this is comprised of the boxes typically which you see here. Like there is a perception system which tries to make sense of all the information it gathers from these sensors. Then a prediction system which predicts how the individual elements which the perception system found are actually moving, because there are pedestrians, there are other cars, there are maybe balls flying on the street from a little child, and although you don't see the child may be running after it. Then there is a planning system which takes the location of the car and the maps and tries to find a route which is safe, which hopefully doesn't kill anyone in the process. And all that is fed into a control system which then does some final checking, engages with a fail-safe operation in case something terrible happens, and tries to shut off the car. Now, for running these kind of components, and they include a lot of AI and image recognition and all these kind of things, you need something like a big desktop in your car, which means there are complex hardware and software systems on which you need to trust in order to get your car driving autonomously. On the other hand, and I will refer to that as the brain of the car, although I'm not convinced that it's intelligent at all. On the other side, you have the driving subsystem, which is actually responsible for motor control and all these things. That's ECUs which we have built since nowadays perhaps 70 or so years. They are connected via robust, simple buses, typically 1 or 2 lines. And I mean, you can try a lot of things, but they are the robust system. We have experience how to build these kind of systems. We don't have much experience how to build the left-hand side. And in addition to the functionality like motor control or battery control, what I will require throughout this talk later on is that we can also maybe follow a trajectory just by using the driving subsystem. Because that's not so complicated. You just get a trajectory, you get your location of the car, at least based on the path which you drove, and then you just need to kick the car a little bit to the left and to the right. So all that you have to do is actually control the wheels in front to turn left or to turn right. The other thing, which I will later assume, is that we have some simple V2X communication. So car to car or car to infrastructure. Because again, putting a TCP/IP stack on that thing is not terribly complicated. Having a sensor like a laser which morses the information to the car in front, it's also not so complicated. So as you see here, the complexity of these systems is quite diverse. We have a huge complexity on the left-hand side and something really manageable on the right-hand side. Now, of course, I have been asked what happens if someone breaks into the driving system. And fortunately, if you just look at the existing technology which is out there, there are already systems like the RC3 core which provide us everything which we need. They have 3 cores. They have they run at 200 megahertz, which is enough for driving. It's far from even thinking about image recognition. But essentially, you get these things qualified for high safety levels, and you can use them for arbitrary things. Now, of course, what we want to use them for is fault tolerance. So just let me put up the two definitions here. So fault tolerance is the ability to deliver the intended outcome despite adverse cyber events. And resilience is the ability to recover from or adjust to misfortune or change, or the property of resuming the original shape or position after being bent, stretched, or compressed. So something like elasticity. Now, if you attach the word cyber, then that means our system should kind of morph around the cyber attack which is happening, and in order to kind of stretch around it and then return back into the original shape. So I think these definitions are quite good and give us a quite good analogy what we want to achieve in the end. And essentially, cyber resilience is there to deliver us continuous fault tolerance. Because with fault tolerance, we might be able to absorb a fault, an accidental fault. We might be able to absorb an intrusion, so something with some malicious mind or intention behind it. But we are losing resources in the process. So in the end effect, what is happening is we need fault tolerance to buy us the time for establishing the resilience, for bending our system, for morphing our system, for re-establishing the functionality. And we are losing resources in the process. Paulo mentions this magic number like 3f plus 1, which means essentially to tolerate f faults, we need 3 times as much and then one additional replica to compensate that. If one fault has happened, then we have 1 replica less. So if the adversary would simply continue, then over time all the resources are lost. And that's where resilience kicks in to recover these resources and to recover what we have lost. So now really in an attempt to explain you how it works in a minute, probably I need a bit more. So assume you would have these n replicas, and then what you ask them to do is implement me some kind of functionality, here denoted by this little function f. Now in case they all receive the same inputs, then in the absence of faults, what you would expect is to get identical outcomes of all of them. Which means you can simply take n minus f, identical of these outcomes, because then you would be able to tolerate up to f faults in such a system. Like replicas implementing a different function based on the inputs which they receive. Now, of course, all the replicas in this picture have the same color, which means they are identical. They run the identical software stack. And while accidental faults like an alpha particle hitting a certain memory cell are stochastically distributed, me as an attacker, I would of course go and try and apply the same attack to all the other replicas, which means first I eventually get the majority, and then I might even be able to compromise all of these replicas. So that's not how it works. What we have to do instead is we have to instantiate slightly different replicas initially by providing the same functionality but with different solutions, different versions, different alterations of how we get to that functionality, how we get to that result. And then what we can do is we can start thinking about repairing the replica which has been compromised, replacing it with something which has yet a different color, which is diversified, so that the adversary cannot simply replay the old attack and try to catch this replica. So now, as long as the adversary is slower than we are repairing these replicas, rejuvenating and diversifying them, then we have an edge over the adversary and we can tolerate cyber attacks essentially forever. The problem now is if the inputs can differ, like if, for example, a client in this case can inconsistently lie what the replicas should do, then, of course, what is happening is that the replica on top will produce one version, and in particular it might be stateful, so it might embed something based on this computation in his state, whereas the other replica would do something completely different. So in this case, we get to the magic number that Paulo already mentioned. We need 3f plus 1 replicas, because now in the first step we would need to agree on what is the operation which we actually want to do to avoid this equivocation effect which we had in the beginning, and then we go to the result and finally update it. And in that case, again, we can tolerate f faults. Now, as I mentioned initially, for autonomous driving, replicating on the right-hand side some driving functionality 3 times because we get some reliable checked information from the control system, that's doable. We already have the 3 cores on the RX. Replicating the brain 4 times, That's extremely costly. Like Tesla is currently charging what, 15,000 just for the promise of eventually giving you autonomous driving functionality, paying instead of 15,000, 60,000. That's quite a ballpark. And I mean, even it's not worth 15,000 what you currently get. But let's focus on the ECU side first. Now, the first part is we need to cheat a little bit in order to bring the costs down. Of course, we could run on the ECU side, so 2F+1 or 3F+1 replicas, but still it's costly. It's costly in terms of energy, it's costly in terms of runtime performance, and so on. And plus, think of this diversity. We need to hire 3 teams initially to build us the 2F+1 replicas and so on. So fortunately, Martina and her PhD student came up with quite an interesting insight. Most of the plants which you are using in your daily system, most of the systems which you control, have an inherent stability, which as long as they stay within a certain region around the stability point, they can tolerate some deadline misses. So the most simple thing to get this insight is by simply realizing that most of our computers are currently so fast that we can simply oversample the plant. We can actuate the plant, sense and actuate the plant much more often than the Nyquist theorem would require. And in that sense, we would be able to, of course, miss some of the control task deadlines. Martina worked that out completely. Don't ask me about it. I'm not a control theory. Just look at the paper. She knows everything about control. But the nice thing is, from the result in the paper, we can design controllers for the individual plants so that if we don't disturb the plant with wrong outputs, we can still kind of retain stability of the controlled thing. So in this case, for example, an inverted pendulum, even though we would miss some of the deadlines. And now this, of course, allows us to reduce the number of replicas which we need. So how do we do that? We assume now we want to tolerate 2 faults. If we go for 2F+1 replicas, which means we are assuming still that all the replicas get the same inputs, then, of course, we would try to reach agreement, and we would ask for n minus f matching results. So with f equal 2, we would need 5 replicas normally, and out of the 5 replicas, we would have to wait for f+1 results, which means we would need to wait for 3 results. And therefore, since I promised I wanted to cheat to get down to f+1, we just executed with 3 replicas. So you have here 3 different controllers, slightly different implementations, implementing the same functionality. And of course, what we can have is we can have a cyber attack, like the middle one, and we can have an accidental fault, like the bottom one. Now, all of these controllers, I mean, the compromised ones, they can behave as in an arbitrary manner, not so arbitrary, but mostly arbitrary. But maybe they give us a control result. Like, for example, the pendulum is bent slightly to the right-hand side, which means we need to accelerate the car to the right in order to stabilize the pendulum again. And the correct controller would give us this output. It would say, okay, our actuation signal should be A, and we want to drive that way. The other 2, because the blue one is compromised, the yellow one has an accidental fault, like a bit flip somewhere, they come up with different results. And so we can't draw a conclusion at that moment in time. We will miss the deadline. We can't reach agreement. So let's try again and assume we would have a very, very, very fast way of rejuvenating these controllers. Like, we would be able to kick out the adversary, to re-instantiate them, to repair them completely. But then, of course, in the second epoch, things might go wrong as well. Most systems, most real-time systems, like your clock synchronization algorithm, which is implemented in your cars, assumes that there can be 1 accidental fault every 2 epochs. The coverage of that is just by statistical analysis, and it can, of course, happen that you have 2 synchronization faults following in every epoch. So for that reason, we want to tolerate essentially accidental faults up to f of them in each of the epoch. For cyber attacks, I mean, the adversary needs a little bit of time to analyze our replica, what is running, and so on. So maybe he found already a compromise for the red version of the controller and for the blue version, but he will still need a bit of time. So we tolerate malicious faults in addition to the accidental ones, where up to F replicas can be compromised over this period of F+1, which we will see in a minute. So now the end effect is, and that's where the cheating starts, we will get results. The compromised replicas, where the adversary has actually managed to break into them, they might agree, of course, on the result, because there is this intelligent being in there. And of course, also the correct replicas would agree with the correct result. Like the correct replicas would say, car, go to the right, whereas the adversary tries to go to the left. Now the cheating is starting because with the accidental faults, we cannot allow the accidental fault behavior to be so predictive that the adversary can actually predict what the accidental fault will be and produce the same output. Because otherwise, of course, you could immediately get a majority and then kind of steer the car into the wrong direction. This is, of course, quite a harsh assumption, so that's part of the cheating. We can further complicate this by asking essentially all these replicas to solve a challenge response problem. We simply give them a random number and they should return the control result with an XOR with this random number, which means you now need a correctly executing replica which still has an accidental fault. So we can kind of make it harder for these things to happen, but we cannot fully eliminate it. But then assume that the adversary would not be able to guess the fault behavior. We would, in the third epoch, now be in a situation where essentially we have, again, 3 replicas rejuvenated again, and they would now provide us the individual results. And out of these results, we would be able to form a majority over time by simply collecting the results of the correct replicas. They will match the ones with the accidental faults. They don't match by our cheating assumption, and the adversary is able to compromise only 2 of these replicas within that epoch. Now, of course, as I mentioned, we have a bunch of problems here. Namely, one of the problems is this assumption is quite hard, but the other problem is that controllers are typically not stateless. So normally you have really state in your system which you need to carry from one epoch to the next epoch, from one control invocation to the next one. For example, if you use a PID controller, which is one of the most common things, you need to carry over the error and you need to carry over the accumulator to compute the integral and derivative part. For controllers which are seemingly stateless, like linear quadratic regulator, where you just have kind of a forward matrix multiplication on the inputs, even then you can run into situations where some of your parameters which you have in the plant, they are there, but they cannot be sampled. For example, you can have a sensor for the rotation of your pendulum and for the position of the wheel, but you might not get the velocity out of that, the angular velocity or the velocity of the cart. But this is required by the LQR rules for the controller. So in that sense, you would need to memorize the past positions in order to compute a moving average to get to this velocity value. Which means, finally, we have to deal with stateful controllers. And plus, all the interesting controllers, which save fuel, which save battery, and so on, they are stateful anyway. So how do we get to something which is stateful, but which we can treat as if it would be stateless? Because if it's stateless, we can just reinstantiate it. And this is how it works. The first thing is we need a trusted component. And I mean, you have seen the blue thing. If you have listened to Ines talks, that's our symbol for a voter. So it takes the inputs, it seeks for the majority, and then consolidates the F+1 matching results to a single result to invoke the plant. Now, the other part is if you want to trust this thing, you better implement it in a way that it's really trustworthy. So you ideally would put it as a piece of hardware into your system. But then it means control tasks, they would need the privilege to talk to that voter and in particular to talk to that voter through a dedicated interface. Now, if you would change these privileges, first you require a microkernel, at least a simple operating system to perform this privilege change. And also we know how to implement such a system, because that's media, that's what Inch did. You have a bunch of problems. One of the problems is you need to create a replicated hypervisor in order to tolerate hypervisor level faults. The second is, if the hypervisor is faulty, he as well needs to repair itself, which means it takes time. So in the worst case, you try to change such an application by the time when the hypervisor needs to recover and so on. So you have a cascading effect of all the worst case execution times of these individual operations, and that can easily consume all the time which you have in your control task. Now, the solution to that is, let's stick with a fixed interface. Let's simply make the voter aware of the epoch for which the proposal is done, install sufficient buffers so that essentially, even though it's the same task, it votes into different buffers. And then the rest is just make everything read-only. Not everything, because you might need a stack. You might also need to write to the voter interface, because otherwise it would be pretty useless. But also state, which we need to carry from one epoch to the next epoch, that can be read-only. But wait, we want to have a stateful controller, right? So the trick here is we vote, but we vote not only to activate the plant, we also vote what should be updated in terms of the state which is then passed to the controller in the next time. And for that, you just need to change the voter to be a little bit more wide in terms of the interface by not having to vote on a single write each time, but vote on a sequence of writes. The sequence of writes, some of them go to the activator, some of them go to the state, and updates the state in a consensual manner, but of course only after collecting the majority. And then you have essentially everything you need, except one thing. You need to rejuvenate this replica when in between each invocations of the control loop. So here is how a normal control loop looks like. If you slightly rearrange this into a continuation style programming, then it looks more like this. So you have some initialization code which you run once, then you enter the control loop function, and the control loop function just does the normal control loop. With one exception, it asks the voter for which sensor values it should do the computation. The sensor values can then be part of that state, provided by the sensors or provided by such a thing in a previous iteration. And afterwards, it proposes the result to the voter. So what is the new activation value and what is the new state? And then the trick is, by implementing it as a continuation, you never need to return to that function. It never returns anyway. Because what happens is, the next time the thing is invoked, you just jump back to that function and you reset the stack to the beginning. As a continuation, you don't have pending state on the stack. It's illegal to keep stack on the state. Okay, so we implemented all that. We, of course, use the most severe and critical resource, our coffee cup, to test the system. It's really robust. It's running with F+1 replicas on the Linux system. You can, as Alexander will show you, also pour water. We didn't dare put in coffee because of the stains and because of the carpet. We also have, unfortunately, carpet always. So it really works. You can inject faults up to F. And the thing is surprisingly stable, even though the underlying operating system, which we used as an implementation vehicle here, although it could be implemented in bare hardware, is quite unreliable in terms of timing. So it works out. So now, after solving the ECU part, let's have a look at this part. And the key insight, and remember, we don't want to replicate that part 3F+1 times. The key inside that part is, what happens if you're alone on the road? What is your safety functionality? Yeah, I mean, you drive a little bit, you stop, should be okay, right? You are alone, so finding a fail-safe maneuver and executing that is quite simple. The situation is quite different if there are a lot of cars on the road. But if there are a lot of cars on the road, I mean, the task gets more complicated, but then we also have the brains of these cars available. So now the trick is, we would use the brains of the other cars to help out the car whose brain has failed. So we call this car the brainless car because it got compromised. We don't allow the adversary to compromise the driving system. That's by our assumption. And I mean, media and all the other stuff, replication of the ECUs thing which I just showed you, that gives us a little bit of confidence at least that we can eventually write something like an intrusion-tolerant driving system. But of course, we give up on the autonomous part. So the brain can be compromised quite easily. In particular, if you think of over-the-air updates and managing to install an insider into Bosch or something like that. Now, the trick how it works is, if you have a car and you look at your ego view, then the helper car can simply project its own view to the view of the other car, and then essentially use the same software stack as it is out of the box after this affine transformation to compute everything for the other car. So you could just re-instantiate, and that's what we did, part of the software stack. So you start with your own prediction and own perception, because, I mean, that's what you need to do in order to understand your environment. But then you perform this affine transformation. You project yourself into the other car and just rerun some of the tasks again. Yes, you might need to analyze more objects, because objects which are outside your safety critical zone now become part of the safety critical zone of the other car, and so on and so forth. But in theory, it works out. So let's see whether it works out in practice. Now, of course, then we would have a trajectory for that car. And the idea is, if that trajectory would be trustworthy, we can just ask the driving system, hey, run this trajectory instead of the trajectory which comes from your own thing. Now, of course, the other car could be compromised as well. So we might have up to F of these cars surrounding the vehicle which is in need of help being compromised. So it doesn't work that simple. Now, of course, the standard solution which all the car vendors try to sell you is use the roadside units. Roadside units are nice things. They are fixed installations near the road. They run a computer system. They are as accessible as your car, because if you park your car somewhere and then some adversary can go in and hack the car through the mirror and enter through the CAN bus and so on, they can easily open such a box and carry it. And if you use it for precise location information, like augmenting the GPS signal, just moving it 5 meters to the left or to the right already helps jeopardizing the information that the car receives. So from our perspective, roadside units is just like something like a boring car. If you have a lot of problems, then of course this infrastructure helps, but it helps only in the sense that you have an additional unit which you can ask to compute something, but it might fail as well. So now, what we need to do, of course, is run a consensus problem among these vehicles. And it turns out that the consensus problem which we actually have to solve is quite trivial. Because normally, when you look for consensus, like you try to reach agreement on the operation which you want to perform, then it's quite a lengthy protocol where you seek for exactly one total order in which operations are executed in order to maintain the notion of a simple state machine. What we need here is just any trajectory which is valid, which is safe. So what we can do is, if the car in need, so the top one, asks for help, then all the cars in the surroundings, they can compute a trajectory. And hopefully they will compute the right trajectory. Then in the next steps, they just broadcast this trajectory and say, that's my proposal, how I would help you. Now, of course, we need consensus, which means all the other cars take these trajectories and validate them. They check whether driving along this trajectory will lead to a safe state, assuming the ego view which they have. Which essentially means we need to check whether it starts from the correct position, where the other car is. We need to check whether there is no collision on the way. And we need to check whether finally we reach something which ends up in a better state than we are currently. And then we hope that we get an update soon enough. Or ideally, we would find a position where we can safely park this car. And remember, in the initial scenario where we are alone, we can just drive and stop the car in the middle, because we are alone. We see that the other car is far away when it stops on the road, so we can react to that. If we are in the crowd, then maybe better we finish the takeover maneuver of the truck and then park it on the side lane or so. Don't construct cars without a side lane. It's a bad idea. We need them. And then, of course, what does the car do? I mean, all the helping cars, they just signing trajectories which they deem valid, which they checked for correctness using their brain. So the only thing which the actual car in need needs to do is to validate whether one of the trajectories has received F+1 signatures. Because then we know that at least one healthy car confirms that it's a valid, correct, safe trajectory to follow. And we don't care which one it is. That's the insight. We just need any one safe thing to stop the car somewhere on the side lane. And that's quite interesting. Now, of course, we implemented all that in the Apollo driving stack. We have a simulator which gives us a virtual simulation of the environment where the car is taking sensor values and so on. That's currently Kala, which we are using. We are using Apollo, which is actually the stack in Baidu and in Huawei cars and so on. And what we've done is we just kind of simulated a bunch of scenarios. You should be within 20 meters to help out the other car. That's one of the insights. The other insight is, if we have a full connected network, so if we are in a populated situation, if enough cars are around, then of course we can easily handle that situation by reaching consensus. But even if not, if the situation becomes more sparsely, if the road is sparsely populated, then our connectivity falls and we can still reach consensus in some situations. And for those where we can't reach consensus, we have at least a probabilistic guarantee. But remember, these are the situations where it's behaving sparsely. Now, we tested that for different Fs, for different things, and we did a Monte Carlo simulation up here, just to see how far we can get, how the asymptotic behavior is. And it looks quite nice. So hopefully, we will be able to write this up soon, publish it somewhere, and then I can send you the paper. Now, how much time do I have? 10 minutes. 10 minutes, that's good. So, good. So, as I mentioned, that was, so that was my part on autonomous driving. We are also sometimes working on completely different things, and I thought, like, let's at least share the basic insights of one of these things, and that's hierarchical consensus. So the problem, again, is we want to reach consensus. In this case, we want to reach consensus in a setting where we have clusters. So you have maybe a data center, or you have multiple data centers, actually, and you want to make sure that your transactions are durably recorded in these data centers, which means if it's bank transactions, you want to be sure that your money, you received all the money which you are supposed to receive, and that even if one of these data centers burns down, that you still kind of have a positive bank account in the end. Now, within each of these clusters, up to F replicas can be Byzantine. And in addition, we want to tolerate these cluster failures. Also, we are looking into situations where clients might have a favorite cluster, like, for example, the data center near him or the bank in the same country. But de facto, we want to reach kind of global consensus, so, and in particular work on data which is not naturally sharded, where you don't have an association of which data center handles all the transactions for a given client. So most of my transactions are maybe transactions in Germany, because that's where I'm living, but occasionally maybe I transfer money to Paulo or vice versa, hopefully vice versa. Thanks. Now, in that situation, we need to reach global agreement. And what we have looked into is, can we just reuse the existing protocols? And there are some interesting insights. We have tried to use, there have been works like Stuart from Yair, which looks into hierarchical stacking of PBFT and of other things, so homogeneous protocols. But what we tried is it actually possible to use a hybrid protocol, a protocol which requires a trusted component? And in this case, we use dummies as an example. In addition, we used hot stuff, and we realized that we don't need all the phases for hot stuff, And actually, the only reason why we have been using hot stuff was we wanted to be able to early on decide whether we have conflicting transactions or not. Without that, we would just kind of run only the global protocol and only this cluster confirmation. Now, one of the two key insights is the fact that we force a replica to get confirmation for all the critical operations that it wants to do, all the operations of the Damocles protocol, from all the other members of its own cluster, of the local cluster. This replaces a trusted component in most of the useful efforts. We can't put in a single key and keep confidentiality of the information. We could do secret sharing, of course, but we can't kind of use something like the USIC where we have a symmetric key. So we are stuck with public key crypto. But aside from that, cluster confirmation gives us exactly the same properties as the trusted component would give us. So I can guarantee that we get a sequence number, for example, that we get the accumulator in Damocles and so on. So it's essentially you can use cluster confirmation as a replacement for a trusted component. Now the other thing is, you might run into situations where all your global replicas, all the replicas which participate in the global protocol, which represent their clusters, are Byzantine. Because, I mean, for whatever reason, we selected all the red replicas to run Damocles. Now, they need cluster confirmation, which means they can't do bad things, but they can, of course, not do anything. They can kind of just decide, okay, we skip, we don't execute blocks, and so on. So in that case, what we need to do is we need to find a rotation scheme, and this rotation scheme cannot simply be a rotation scheme within the global protocol because it's currently dominated by the compromised replicas. So we would execute Damocles with all faulty replicas, and we can't get out of that, except if we accept a rotation scheme where essentially all the replicas can claim that something goes wrong, where the other replicas can trigger the rotation. And now, a simple rotation scheme in that kind of scenario doesn't work out. Because what can happen is that if you would say, for example, you select always the first replica from each cluster, then the second replica, and so on, then with cluster crashes, you can essentially run into situations where you only one out of all the other combinations will find a cluster which works out. We fixed this situation by requiring actually F+1 replicas to participate in a certain step of the protocol, so that more replicas know what is happening. You can also fix this, and that's in the current version of the paper which we have submitted, by simply saying, okay, you do a full permutation of all possible combinations, so that's still a weakness of the paper, but at least we know how to settle it. Okay, and I mean, with that, I'm ready to conclude my talk. It's worthwhile looking into application-specific fault and intrusion-tolerant protocols, because, for example, you can build something for a control task which has this inherent stability to reduce the number of replicas to F+1 replicas. It's also interesting to look into autonomous driving. I mean, the side effect is you really get scared of autonomous driving. But at least it's raising some interesting problems, and sometimes the solutions are much simpler than you thought. So safety under attack is actually easier in the crowd than if you are alone in isolation. But then in isolation, it's also less relevant. And the last part, it's really fun to also look into the large-scale stuff, because sometimes you can learn from the small scale for the large scale. Like, for example, how to replace the trust components and with something like cluster confirmation. And the other way works also. So with that, I told some of you that I have one additional experiment, and the assumptions for this experiment are as follow. I assume that this is the brain. It works. I have a reliable driving system, and therefore I have done the last measurements this morning. So here is the measurement which I have performed. The rules are you start at the hotel or you start here at the parking lot. You race as fast as you can, but safety goes first. So you stop at stop, you adhere to the traffic lights, you don't crash into things, you don't hurt anyone. The rest is up to you. So these are the high scores which I did yesterday and the day before. Yesterday evening, Ines prevented me from actually doing that route because we went for dinner. But this morning, I actually managed to avoid one of the traffic lights being red. And here is the current high score. And of course, I like to see how this figure evolves. Okay, thanks a lot.